हाँ देख दिल सेल्फ
No, no,
स्क्रीन है।
Sir, good evening, sir. Just 2 minutes, sir. Just now class over. Hello.
Arunachalam sir, I think sir also just went somewhere again.
No problem. Okay.
Okay.
Right. Thank you.
कंप्रेशन रेट
Vignesh, can you mute it? Vignesh.
setting hello on count
கால் பண்ணி சொல்லுங்க.
இன்னும் முடியல இந்த பாலா பாயிண்ட் வைஸ்ல டிஃபரெண்ட் இருக்கும். CO. Yes, இன்னும் பண்ண சொல்லிட்டு எல்லாம் அவங்க வந்து அவங்க ரெடி பண்ணணும். இது இல்லை இன்னும் லைட்டாக அதை வேலை எதுவுமே பண்ணாமலே.
Okay, good evening. Shall we start the class?
Sir, good evening, sir. We can
Ah.
start, sir.
Okay, thank you.
One of our students is not muted, so I asked him to mute.
Okay, okay.
Sorry for that, sir.
No.
Sir, I have a question, sir.
Yes, please.
Sir, this came up during one of our vehicle trials or something. So in one of our ECUs, we were using some motor,
Okay.
and they were talking about resonant frequency there, sir. So like for NVH purposes and all, they talk about resonant frequency to ensure that vibrations are not too much whenever the motor is turned on or something. So how do we calculate this resonant frequency? And like, how do we adapt it, sir? Like, because motor will run at higher speeds and like in varying conditions, right? So can you just help me understand, sir?
Okay. That is basically depending upon the mass of the moving parts, overall mass of the motor. Correct. So you are talking mechanical resonance or electrical resonance?
I think mechanical resonance, because this is with respect to NVH, sir. So they were like,
In that case, the rotating part mass, no, the vibration is created due to rotating part mass, and that depends upon natural frequency of the system. Natural frequency of the system depends upon the stiffness and mass. Correct. I mean, mechatronic we have talked about, no, natural frequency depends upon the mass and the stiffness of this one, and what is the excitation frequency. Correct. So that means you are going to given the structure. If you vibrate the structure, the vibration happens because of rotation in the motor. That is due to motor speed. Correct. What speed? Because you have a motor which start something from say 0 RPM to say 5000 RPM. Correct. At a motor will start vibrating more for particular speed of the motor. That time the moving parts goes to resonance. Right. That is called mechanical resonance. That you should not operate. Generally, when you operate your machine, you should operate your machine lesser than this resonance frequency. Up to 80% or 85% only you should operate. So if resonance frequency of the motor or the engine or rotating part is, say for example, 5000 RPM, you cannot go beyond 4000 RPM. If you operate a resonance, the mechanical structure will break. Resonance can break your machine itself. That depends upon the mass and the stiffness of the moving parts.
Okay.
Correct. The moving parts are excited by the rotation. Of course, if it is electric motor, that depends upon voltage and your supply. DC motor voltage decides the speed of the motor. No, speed of the motor. DC motor depends on voltage and current applied to the field and armature. Already we saw the equation. So that means you should never run your motor at that speed. At the speed, the mechanical mass and stiffness start resonating. So you should not run that. That what you will do is you put your machine, put the sensors to measure the vibration, amplitude, and when you vary the motor speed, after fixing everything, you will see that there will be a vibration picking up. But once it goes near the resonance frequency, that purely based on stiffness and mass of the rotating parts.
Okay.
Okay.
Thank you, sir.
Okay, fine. Okay, so we start that. Now, in the previous class, we talked about induction motor. Today we are going to see another type of induction motor, and one DC motor, this one types of motor. So the motor what we are going to talk today is a permanent magnet synchronous motor. Please note that we start AC motor, we started with synchronous motor. Synchronous motor, yesterday I told you that it has a 3-phase winding which is supplied with AC voltage, 3-phase AC voltage, which generate rotating synchronous magnetic field. The rotor is a DC magnet. It will be supplied with DC voltage. Because of that, the rotor will, north and south pole will get locked with rotating magnetic field, north and south field. Correct? We already say there's a vector, how the resultant magnetic field start rotating. I showed the each different angles with respect to 0 to 360 degree. When three-phase voltage is varying, because they are separated by 120 degree, we saw that. The stator is a electromagnet, but it is a DC magnet. But the north and south pole is fixed. And it will get locked with rotating magnet, it rotates. That's how the torque is produced. Then we saw the induction motor. In induction motor, rotor is just coil. No magnet, no permanent magnet or no DC magnet, only a coil, short circuit coil. Yes, please.
Sir, same slide or you are changing?
No, I have not changed. I have not changed. Just generally as talking.
Okay, okay, sir. Okay.
So that is called induction motor. Advantage is rotor is just made of coil, two type of wound rotor, and we saw the equation, many how to control torque, everything we saw, equation problems we solved to find out the synchronous speed, all these things we saw. Now we are seeing third type of motor, which is popular in electric vehicles and also in the CNC machine, all those things, which is called PM, permanent magnet synchronous motor, or PMSM. Short form is PMSM. It is also AC motor. If you say AC motor, automatically input voltage is AC voltage. So this picture shows that cross section we have PMSM motor or permanent magnet synchronous motor. Permanent magnet consists of a permanent magnet rotor. Correct? Rotor is a permanent magnet, not a electromagnet like in a synchronous motor. Please note, this is also called synchronous motor. Only thing is the rotor is a permanent magnet, not a electromagnet. Okay. So then, of course, it has a starter. Please note that any motor means you need two magnetic fields which interact with each other, attract or repulse. Correct? Two magnetic field which may attract or repulse each other. So torque is produced. If torque produced is able to move the rotor. See, stator is fixed, it is bolted. Body of the motor is bolted, nut and bolt on your bed. Correct? The stator coils are in the periphery of the stator. Correct? This is the stator. Correct? So you can say that this is the stator body, or stator, which is nothing motor body, in which there are slots. In the slots, you have coils. These coils are supplied with a voltage. It can be a DC voltage or AC voltage. With a DC motor, it is called as a field coil. If it is AC motor, it is called as stator coil. Correct? Field coil, stator coil. In case of field coil, there's one set of coils only. Correct? Depending on number of poles, pole pair. Correct? You supply voltage to the poles. And the DC, the field is created. Then you have a rotating part. It has a coil. We call it armature. That also you have to supply. That means you need two power supply. One is called field voltage. VA is armature voltage. Due to that field current, due to the armature current, due to this field flux, due to this armature flux, these flux will interact each other depending upon the polarity. If a field polarity is not nearby, the armature pole is south, it will attract each other, they try to align. So the rotor will try to align, the armature will try to align, torque is produced. So that's how the torque, if torque is sufficient to overcome the friction in the bearings and inertial load of the armature itself. Armature is a mass and you are connected to load. If you are able to overcome the inertial and frictional loads, then the armature start rotating, it speeds up. The speed increases, and already told you that the speed will reach only particular zone depending upon how much torque it can produce, and also self-regulating. That is different. So you need two magnets. Similarly, in the AC motors also, you have a stator. It produces a rotating magnetic field. Correct? Then you have a rotor, which is a DC, it's an electromagnet. Both get locked and start rotating. Already we talked about synchronous motor, how it works. This is a permanent magnet synchronous motor. Only it is a synchronous motor. That means it has a rotor coil. Correct? stator is body. Inside that you have stator winding coils, correct? This is a three-phase coil. So you supply three-phase voltage, correct? So again, it creates rotating magnet. Stator in permanent magnet synchronous PMSM also creates a rotating magnetic field. The only difference with synchronous motor in this is the rotor is made of permanent magnet. This is a permanent magnet, correct? It is not electromagnet. That means there is no need to supply voltage to the rotor. This is what differentiates the synchronous permanent magnet synchronous motor from regular synchronous motor. In regular synchronous motor, you have to give two voltages. Field coil, that is a rotor coil with a DC voltage. Stator coil with three-phase voltage. Permanent magnet synchronous motor, stator will be supplied with three-phase AC voltage. Rotor is a permanent magnet. You don't need to supply the voltage. So complexity reduced, correct? There is no need for secondary one. Then to supply the voltage to the rotor in synchronous motor, because the rotor is rotating, so DC voltage supply, you need slip ring, correct? Slip ring is additional mechanical device attached to the rotor of the synchronous motor through which you are supplying DC voltage. And there will be brushes, correct?
Sir, I'm sorry to ask you one question, sir. You have just told
please.
that in the conventional, what I mean to say is synchronous motor, the AC is supplied, rotor coil is supplied with DC current and the stator is supplied with the AC current, right?
Correct.
Three-phase AC.
Yes.
Is that other way, sir, or I'm sorry, just asking.
No, it is correct.
Okay.
Stator is a three-phase, which is in the body.
Okay.
Three-phase coil. The distributed in slots. It is like this is what this stator coil.
Okay.
Correct. This is supplied with three-phase voltage.
Okay, and rotor is with apna DC voltage.
DC voltage, because of DC voltage, it produces the DC magnet, electromagnet. That will get locked, correct? I told you, for example, you have this is phase 1, that is A phase. I say this is second coil. This is A, I say this is A dash, correct? And this is B, the second coil, B dash. This is C. Yeah. I think I made a small mistake. Let me correct it. 1 minute. You remember, but sorry. So this is one coil, that is three-phase, no? After that, three-phase, this is, I say, A, phase A. RGB we said. I told RGB. Sometimes some book called as ABC also. I say that this is R phase, and the coil comes, and exactly these are the pair, correct? So this coil comes under this one, and second coil I say B. So this comes to this. This is the B, and third one is C. That is green, G. Correct. So we together is called a pole pair. There are 6 pole, 3 pole pairs are there. Okay. Then the rotor is a permanent magnet, that is electromagnet. Right. There's a coil. The coil will be connected to a slip ring mechanism through which DC voltage is supplied. So this is a mechanism, slip ring mechanism, which is part of rotor, plus minus, this is a DC voltage. So this produces north and south pole, this is always fixed. Okay. Then here, this creates a rotating magnetic field. As I explained, rotating magnetic field is created because we are given this one. So what will happen when this is south pole, this is north pole, these two are locked, correct? So as the voltages are varying in 3 phase with 120 degree apart, correct? Already I told you that this is RGB, the resultant magnetic field already we talked. Correct? Each time instant this one. So the permanent magnet, that is electromagnet of the rotor get locked with the rotating magnetic field. So when this one it rotates, that's how it works. So there you have the electromagnet. But in case of permanent magnet, this is a permanent magnet. Permanent magnet rotor. Otherwise, both are same. Stator is a three-phase coil. Three-phase winding with coil. Same as this one. Now, so because of this, I am using a permanent magnet. One power supply is not needed. Another thing is you don't need slip rings. Correct? Slip ring means additional mechanical. Slip ring will also be worn out after 1 year, 2 years, depending upon usage. If you use motor continuously, rubbing due to wear and tear, rubbing of the slip ring, there's a brush and mechanism which touches supply. So slip ring has to be changed every 2 years, one depending continuous, all those things, and it cost the maintenance down, all those things. That part is automatically removed in permanent magnet synchronous motor compared to conventional synchronous motor. Correct? So you have three-phase stator winding, which is supplied with three-phase AC voltage, and rotor is a permanent magnet. So it simplifies. So here it is shown with single. This is rotor with having a single north and south pole. But here you have multi-pole, correct? So each one is a, please note that the projections, correct? Each one is a magnet. Correct? So multiple poles are there, advantage is there. Smooth operation, all those things. Right now, for understanding, you can forget about this. You can take this itself. With a single one, permanent magnet having north and south pole is our rotor, and you have three-phase magnet, three-phase stator coil supplied with the voltage. There's a rotating magnetic field. Basic working principle of the permanent magnet synchronous PMSM is same as synchronous motor. Stator winding is energized by AC voltage. It generates a rotating magnetic field. When the rotor, now the rotor is a permanent magnet. Please note that already, if you remember correctly, the synchronous motor will not start on its own. You supply three-phase AC voltage to stator winding. So rotating magnetic field created. And you supply DC voltage to rotor. So electromagnet is created. But they may be out of phase with each other. I said magnetically, the rotor should get locked with rotating magnetic field. That means the first what you have to do, you have to have additional one more external motor connected to synchronous motor shaft or rotor, and that motor will rotate the rotor to the speed of synchronous speed. Already we know synchronous NS equal to 120 F divided by P. Already I told you that in India, 50, correct, divided by 4. From this, we can say that it is 12.5. So you will get, okay, I can use 120. This is 3. 30 into 50, easy. 1500 RPM, correct? The NS is going to be 1500 RPM. That's what the synchronous motor will do. The magnetic field, NR equal, already we know, 1 minus S into NS. So the rotor speed will be less depending on the slip. Higher the slip, the rotor speed will be same as lesser the slip, correct? Lesser the slip, the rotor speed is same as synchronous speed. This already we know it. Okay. Now, what I want to say is, now, even the synchronous motor, first you have to rotate the rotor magnet. Even after giving the DC voltage, the rotor in synchronous motor, you have to rotate the rotor so that the speed is close to synchronous speed. The rotor is mechanically rotated such that it aligns with, for example, at a given instant, this is the north, this is the south, this is stator magnetic field. Correct? Now my rotor is something like this. I have a coil and this is south, this is the north. Please note that the magnetic axis for the field is like this, the rotor is like this, there's an angle. And this north is attracting, correct? The north pole of stator is attracting south pole of the rotor. But if sufficient torque is not there, too much gap, the angle is too much, it may not get locked. So that means what you have to take is, you have to physically move the rotor such that the rotor will be aligned like this. This is south pole, north pole, these two are locked. After that, you can do, this will start rotating, rotor will start rotating along this one. That means initially you need a starter motor, additional motor to run the synchronous motor to bring the rotor close to synchronous speed. So the rotor magnet get locked. After that, you can remove external small motor. So synchronous motor will start rotating, then you can connect your load. Please note the load cannot be connected directly before the motor reaches, the rotor reaches synchronous speed, get locked. These are the one of the few things you have to note down in case of synchronous motor. Okay. For that, they have made additional arrangements. So they put what we call as starting coils. In synchronous motor, they add starting coils, which will make the in the poles of the rotor, so that will be an energy apart from the rotor coil. In synchronous motor, you have additional coils which is called starting coil, which is also fixed on the surface of the rotor, and it will be energized. So that will generate a magnetic field, and that will make the rotor to get aligned, get magnetic lock. After that, that power can be stopped. Correct? You don't need external motor. Instead of that, the coil voltage can be, starter motor coil can be stopped, and then synchronous motor will work. So similarly, this whenever you say synchronous motor, it won't, we call it self-starting. Self-starting is not possible in synchronous motor, whether it is a regular synchronous or permanent magnet synchronous. So you give voltage 3-phase, the rotor will be rotated, the permanent magnet rotor will be rotated, so that NS will be same as NR. Correct? Speed of the rotor will be same as this one. Then it gets magnetic lock. After that, the motor, if you change the frequency, the rotor speed will change. That is rotating, NS will change, automatically this happens. So it is energized by AC, rotating magnet. Rotor reaches synchronous speed by external means, and rotor magnet will get locked. And with rotating stator field, they reach a synchronous speed. After that, you can remove the external. Yes, please.
Sir, where is this type of motors application is there, sir? Because
Synchronous motor is for power factor corrections. Power factor corrections, they use it. And the permanent magnet motor is used in electric vehicle. They are trying to use the electric vehicle also, they use.
Okay,
Synchronous
sir,
motor.
Can you explain the second point, sir? Still, we are not getting it.
Which one?
The second point, when rotor reaches synchronous speed, the rotor magnetic poles get locked
with the rotating magnetic field, north and south pole.
Rotating magnetic field of north and runs at the signal speed.
Synchronous speed, NS. See, please note the magnetic field is rotating because you supply 3-phase. Because already I told you, you are supplying 3-phase voltage to the stator winding, which are separated by 120 degrees apart. Correct? So this is A phase, this is B, this is the C. The phase difference 120 degrees. Because of that, at any given instant, 2 phases will be acting, and I told you the magnetic flux generated by each phase. This is phi A, this is phi B. Okay, so and phi C is 0. At any given instant, this is the instant. This is 0 angle. This is 60 degree, 120 degree, 180 degree, like that. This is 360. Correct? Already showed. So at any instant, 2 magnetic field will be working. Third one will be lesser compared. So you get a resultant magnetic field. Please note that this is the arrow shows the strength of the magnetic field phi A. This is phi B, and because both are working together simultaneously created, I get a resultant magnet. This is called phi resultant. This magnetic field is phi S. So this is north pole, this is south pole. Then I have my rotor. Correct? The rotor is get locked. This is, for example, this is south pole, this is north pole, this is south pole, this is north pole of the rotor. Rotor is this one. So that means these two are get locked. Now it is rotating. Then the rotor will rotate. That's how it works, synchronous. So once get locked, the field, the resultant magnetic field is rotating 360 like this. At any given instant, 360 degree. That's what I showed you. Okay, so that's how the synchronous motor works. So only difference is between regular. This is a permanent magnet rotor. Okay, this picture I took it from internet. This was outer, just what looks inner. What are inner parts are the shown here? Correct. You can see that these are coils. Correct. So this is the rotor. And rotor magnets. You can see that these are the rotor magnets. This is rotor hub. Steel plate. This is a because supporting structure, steel plate supporting structure for this one. You can see that this is a rotor with permanent magnet. Rotor with permanent magnet. Having north and south pole. North and south pole, because you know that it has. So this is the stator winding. Correct? Stator winding that is removed for you to understand. So you can see that this is the stator winding. So stator winding is three-phase winding. There's a stator core, that is a steel core. Correct? It is made of steel or steel. Steel itself, you know, it is not iron alone. It is nickel plus chromium plus this one. So it is a magnetic material, and it has slots. Correct? Stator has slots in which you have the coil. Then you supply three-phase voltage. Then rotor is a permanent magnet. It is supported by bearings, steel plate, all those things. So this is how the motor looks. Correct? So now you can see that here there's a cross-sectional view. There are two types of rotors. One is called as interior permanent magnet rotor, IPM. That means interior. Okay, permanent magnet motor, that is rotor, that is IPM. Other one is surface mounted. Surface mounted rotor. The rotor can two types. So stator is a magnetic coils. You can say these are coils, three-phase coils, right? And supplied with three-phase AC voltage. The rotor is a permanent magnet. So if it is a surface mounted, means this is the rotor core, correct? The gray color is a solid rotor core on which you have two halves, correct? Circular, it is a cylindrical, this one. One is north pole, other one is south pole. On the core, they pasted or bolted, correct? North pole and south pole. So this is your rotor. This is called surface. On the surface of the rotor, the magnets are this. That's why you got surface mounted rotor. Permanent magnet. Other one is interior, IPM. Interior permanent magnet. So you can see that magnets are, these are the magnets. Correct? So magnetic poles are inside. Okay, I will show you the next slide so you will understand what it is. Okay, now to understand better, the permanent magnet stator coil winding, how it look, there are two types. Even in case of the stator winding, there are two types of winding. Okay, permanent magnet stator is made of outer frame. As I told you, this is outer frame, correct? This is outer frame, correct? With slots and body and core. Core is a magnetic material in which there are slots in which windings are fixed, correct? These are the windings, correct? You can see the copper windings are there, stator windings. So there are two types of windings, stator winding. One is called distributed winding type stator, note down. Other one is called concentrated winding type stator, correct? One is called distributed winding type stator. Other one is concentrated winding type stator. You can see how it looks. Again, in case of the concentrated winding, you see this is my stator core. inside which only rotor will be there. Inside which north and south pole, rotor is going to be there. This is the stator core on which there are projections like this one, on which coils, correct? So coils are wound over the poles, correct? The whole thing forms the stator, correct? So here the windings are concentrated on the projected like poles. So that's why it's called as concentrated winding stator. Again, it is a three-phase winding only. Please note that this is three-phase winding. And in this case, the coil is distributed evenly. There's no gap. You can see that the coil, this is one coil. You can see that white color is nothing but there's in between insulation. The brown color is a copper coil. There are three-phase coil wound through slots. These are slots. I can put in red color, you'll understand. These are the slots, correct? You can see that in the slots, the coils are, correct? And they are evenly placed, correct? Evenly put inside the slot, so they are distributed evenly, correct? So that's why you call it distributed winding stator. Other one is concentrated winding stator. There are advantage, disadvantage. Okay. So the distributed winding, how it look, you can see that there are three-phase winding, correct? There is a orange color, one winding, black color, other winding, gray color, third winding, this one. And these are the slots, correct? This is the core. Let me clear it, you will see it. So this is the core, stator core, in which there are slots, correct? Grooves. You can see the grooves. In the grooves, the windings are put, correct? They are put equal distance. The grooves are equally spaced. The distance between any two grooves, we say cut section we are seeing. One cut section, correct? You seeing some 10, 15 slots other, in which alternately these are one phase, another phase, third phase, correct? So they are distributed evenly in the equally spaced this one. That's why we call three-phase distributed winding. Okay. Other one is the three-phase concentrated. This is what is shown here. You can see here three-phase. You have the core on which coil is wound, correct? Phase 1, phase 2, this one. The magnetic field created by this will not be evenly spaced, correct? Concentrated weighting will not produce evenly distributed magnetic this one, and the magnetic phase created will be trapezoidal in shape. Correct? The magnetic field created by the concentrated winding will be trapezoidal in nature. Okay? We call as they call it back EMF. They call it a back EMF generated by the concentrated winding trapezoidal this one. For the distributed winding, the magnetic field created sinusoidal in nature. Back EMF will be sinusoidal in shape. Okay? These are the main difference. Because of that, the torque production, smoothness of the motor running, all these things will vary. So there are two types, you understand. One is called as distributed winding type stator, other one is concentrated winding stator. Correct? Two types are there. Okay. The differences between the distributed concentrated winding type coil are the shapes of the back EMF, electromagnetic force generated by the field in the air gap, correct? In the air gap between the rotor and this one, that is going to be sinusoidal or it can be trapezoidal. Back EMF generated due to magnetic field generated by rotor magnets or paramagnetic are cut by the stator windings. The geometric properties of rotor determine the shape of the back EMF waveform. It can be sinusoidal or trapezoidal, sometimes even triangular. Generally, these two are very popular in case of this one. Sometimes, depending upon how the core is, the windings are placed, it can generate even triangular. This is very rare. So, sinusoidal, trapezoidal. Concentrated winding with trapezoidal. If it is a distributed winding, sinusoidal, back EMF pattern will be created. As I told you, distributed winding creates a sinusoidal, this one. Concentrated winding generates trapezoidal type of back EMF. Okay. What is the advantage of this one? More torque is generated if trapezoidal back EMF is generated. That means if I have concentrated winding type of stator, more torque will be generated by that motor. And the copper losses will be more. copper and losses, cost of losses, the copper and lamination will be high in case of trapezoidal back EMF, but more torque to be generated. And higher efficiency is achieved if I use sinusoidal back, that is distributed winding. That means sinusoidal back EMF, making ideal for electric vehicle, correct? So higher efficiency, because we are going to operate, in case of electric motors, we are going to operate from batteries. Battery power you have to use judiciously, you should not waste. So that means higher efficiency means for given out the energy supply better, more distant vehicle will travel. So many times in electric vehicle, they use distributed winding type of stator, which creates sinusoidal back EMF. So higher efficiency achieved. But if I want more torque, correct, at the cost of more losses, correct? Yeah, efficiency losses means the copper loss and lamination loss, the eddy current losses or core losses is acceptable. But I want more torque, energy loss, you can go for trapezoidal winding. The operating magnet in the air gap nearly same as in the rotor magnets, right? So this is another point to be noted. As I told you, the magnet, the stator, you have the slots in which the cores are put. So to create the sinusoidal type of back EMF, this is a distributed type stator winding. Right? You can see that these are the slots. This is the core, correct? This is the core in which there are slots. In the slots, you can see that these are the wires. Correct? 4 slot filled, next 4 slot blank, another 4 slot. The current enters here and comes out through this. Current enters from here, comes out, same coil only. Please note that the slots are, the wires are going like this, it comes out and it comes out like this. Okay. So when you do that, the magnetic field created a smooth sinusoidal. Correct? This is called a distributed type winding. How it look, that's what we said. Oh, the coil winding in stator. Okay. As I told you, sinusoidal means the magnetic field back EMF created by the distributed winding will be sinusoidal nature. This is in trapezoidal nature. This is for concentrated winding. This is for distributed winding. Okay. So now the permanent magnet synchronous motor, rotor, that is a stator. We talked about stator, correct? Stator, the stator is a 3-phase winding. The winding can be distributed or concentrated. Depending upon that, the back EMF generated will be a sinusoidal or trapezoidal. If it is trapezoidal, high torque can be generated, but more copper and core loss will be there. But if it is distributed winding, sinusoidal type of back EMF will be created. In that case, this will be smooth, less losses, and smooth will be the torque generated will be lesser compared to trapezoidal winding. So based on that, you can decide. Then next comes rotor. Rotor, there are 2 types of rotors are there, which is made of permanent magnet, and the permanent magnet made of high coercive force material, generally what we call as rare earth magnet. Even now you will be talking, correct? If you listen about news, Ukraine war, correct? Ukraine war, you can see that recently American president asked for signing a deal with the Ukraine president because rare earth, which is called neodymium, there are some 7 to 8 type of materials. Okay, samarium, correct? Samarium is there, and neodymium. These are called rare earth materials like iron, nickel, cobalt. But for a given size, they can have 3 to 4 times more magnetic flux it can create. That is the advantage of the rare earth magnets. So that means your motor size will be 1/3 size. Instead of using nickel, steel or iron-based core magnet, if you generate, instead of that, if you use rare earth material and create a magnet, the size will be 3 times lesser, lightweight, and the flux density will be 3 times more. Flux density higher means that much power is generated. Small motor will generate 3 times, 3.5 times, 4 times more torque and power compared to conventional DC motor, AC motor instead of this one. So in Ukraine, in the world, the rare earths are available in few places, highly concentrated. One is China. They have 60 to 70% of this kind of material, rare earth material. Next thing is Russia and Ukraine. And of course, in some other parts also it is there. Brazil also some amount is there. In some African country. That's why everybody wants to have that rare earth magnet material. Correct? So that is different. That is not our this one. So generally, you need a permanent magnet that can be made of regular ferrous material, correct? Iron plus nickel plus cobalt, correct? That is convert the motor size will be bigger, correct? The rotor size will be bigger 3 times and more weight, correct? So, but in the electric vehicle, smaller motor which can produce less size, smaller weight and more torque in general, that is what you want, correct? So that means your vehicle will go for longer distance without wasting energy, correct? Mass reduction is important. So modern permanent magnet synchronous motors, the rotors are made with samarium cobalt or neodymium boron iron composition. These are the two. This is a rare earth material. Samarium also rare earth. Cobalt also it is a rare material compared to iron. But this combination are neodymium and boron iron. This combination is used to make the rotor permanent magnet. So it is this one. And sometimes the permanent magnet motors also called a brushless servo motor or non-excited synchronous motor. Please note that already called synchronous motor. Instead of having electromagnet rotor, it has a permanent magnet rotor. That's a different name. Brushless servo motor or non-excited synchronous motor also they call it. Sometimes they call it reluctance motor, hysteresis motor. These are other names of books. That's why I just highlighted. The rotor permanent magnet are made of samarium cobalt or nowadays getting popular is neodymium plus boron iron composition. It is a alloy using that they are doing. Then depending the shape of the rotor, one is called salient pole rotor PSO, permanent magnet synchronous motor, or sometimes they call a rotor also. Correct? They say salient pole rotor, other one is called non-salient pole rotor, used in PMSM. There are two types of, one is called salient pole, other one is non-salient pole. Okay, when we talk about PMSM rotors, rotor types, PMSM with a salient pole rotor, correct, has quadrature inductance is not equal to direct inductance. When we talk about rotor, correct, they talk what you call as inductance. One is called a quadrature inductance, other one is called direct inductance. Inductance symbol is L. The subscript Q means quadrature, correct? Please, then again, L means inductance, D means direct. D means direct. D represent direct, this represent quadrature. There are two inductance in rotor design, and that depends upon shape of the rotor and what angle it aligns with respect to the stator magnetic field. Based on that, the inductance effect, correct? One is called quadrature inductance, this one. In case of salient pole rotor, the LQ and LD will not be equal. Okay, they are non-equal. That's what's happening. With non-salient pole rotor, the quadrature inductance is equal to direct. That means LQ, LD are this. Just information. If you are going to work on the designing of the motor, you have to know more about it. But only thing difference you should know. Exam point of view. And if it is a salient pole rotor, the inductance, quadrature inductance will not be equal to direct inductance. If it is a non-salient pole rotor, then quadrature inductance will be equal to this one. The next one is the permanent will also further classified based on rotor design. Whether the magnets, the rotor magnets are mounted on the surface of the rotor or mounted inside the rotor. One is called surface mounted motor, other is interior permanent magnet, IPM. This is called IPM, interior permanent magnet, or flux concentrating type rotor, synchronous motor, rotor. This is also called rotor, motor rotor. Okay, surface motor. I will show in the next slide. Okay, these are the different varieties of the permanent magnet synchronous motor rotor design. Okay, first thing I want to talk about the surface mounted design. Main classification is surface mounted interior. Okay, so the first top row is called as surface mounted. You can see that this is motor shaft. The white color is the shaft. Right, this is shaft, this is shaft, this is shaft. Okay, there are 4 different type of surface mounted, and this is the rotor core. Correct. The light gray is rotor core, white is the motor shaft, rotor shaft, and the black is the magnets. Correct. Black color is the magnet. You can see that there are 4 magnets mounted on the surface. This is exactly on surface, and they made groove inside this one, and again still you can see that the magnet is on the periphery, outer surface of the magnet. It is like a horseshoe, correct? So it is on surface within the diameter. It is not projecting this one, and here slightly projected, and there are 4 different types of all the magnets are mounted on surface. This is the one type. This is called surface mounted rotor. Magnets are mounted on surface, but you can see that it looks like a pole pieces on this one. Each shape has some advantage. All 4 are this one. Second one is called interior type, IPM. Correct? One minute. The second one not fully, because this is also how the magnet. In this you can see that how the magnetic flux are there. These are also surface mounted. Correct. Wherever LD is less than this one, we can see that that will be interior. Interior magnet means you can see the magnet is inside. Correct. The black color is magnet. Correct. Magnet buried inside this one. This is called as IPM. Interior magnet. I have the rotor core, gray color. Inside it, the magnet is embedded inside, deep inside. Correct. That's why they called as interior this one. So these are the different type of magnetic magnet arrangements in case of the rotors of the PMSM. Okay. Now the surface. What is the advantage of? There are 2 types. There should be some advantage, disadvantage. Otherwise, there is no need to have this one. If you have surface mounted rotor, correct, that means magnets are mounted on the surface of the rotor. What is the advantage? Surface mounted rotor are also called exterior permanent magnet motors, correct, EPM. They produce high flux density magnets using rare earth magnets. As I told you, niobium or samarium or this one, mounted on the solid rotor surface. The flux densities can be generally commercially used motors in this one can be 1 to 1.2 Tesla. You can see that this one. And the advantage of this is uniform magnetic flux is created in the air gap. Correct? You know that between rotor and stator winding, there's air gap. Okay. That air gap, in the air gap only, the magnetic flux are flowing from stator to rotor or this one. So there, the uniform magnetic field is created. Okay, that is one thing. If you use surface mounted, the rotor permanents are moving inside an air gap and close to the stator. The gap will be very small and the rotor magnet very close to stator windings. Operating magnetic flux density in the air gap is nearly same in rotor magnets. Rotor also has a magnet, permanent magnet. It produces a magnetic flux. That magnetic flux will be, density will be same as the stator magnetic field. Please note the stator creates a magnetic field because we are supplying a 3-phase voltage. That magnetic field density will be, because from that it flows through the air gap. Correct? We say that mechanical, the electrical energy is passed to rotor as a PAG. Yesterday also we talked, when we talk induction motor, to the air gap, the power is transferred. There's a magnetic flux, that is called air gap flux. That density will be same as this one. If you use surface magnet type of rotor. Capable of generating very high torque. If I use surface type mounted rotor, those motors can create very high torque and acceleration for the same size, motor size, interior magnet type rotor and surface, same size motor. If you make this motor will generate high torque and high acceleration, and they can be used normal speed, but not very high speed. We say the 0 to 3000 RPM, correct? Something like that, 5000 RPM. They generally operate normal operating speed, not very high speed, correct? 0 to 3000 RPM. They are called low speed or normal speed motors. This motor cannot run for higher speed. If you run in higher speed, they have disadvantages. Air gap between rotor magnet and stator magnet is very small. So the rotor magnets are exposed at all time to the stator winding MMF. Okay. The stator creates a magnetic flux. That flux will be cut by the magnet itself. Please know that magnet, permanent magnet also will cut because it's rotating. It will cut the stator magnetic field. Because of that, there will be a current induced inside the magnet, permanent magnet, that will create heat. And because of all those things, the rotor magnet can get damaged. That is one of the drawbacks of the surface mounted motor if you run at high speed. So that's what we are talking. The air gap between is very close, and the permanent magnet or rotor in surface mounted is continuously exposed to the stator magnetic field. It cuts the stator magnetic field at all times and create harmonics inside the rotor magnets, and the rotor magnet become weak after a few years or few months. So if you run at higher speed, that's why you should not run this at higher speed. It is low speed operation. If permanent magnet rotor have electrical conductivity, please note that the rotor magnet is made of electrically conducting material. I talked of samarium, correct? Cobalt or neodymium and boron, iron, this one. Some magnets material have higher electrical conductivity also. Then they will produce more I square loss because of the induced current. Okay, so because of that, you cannot have surface mounted rotor based permanent magnet but higher speed. Eddy currents are produced. Consider that losses of the magnetic field. That means the magnet torque is proportional to magnetic field of the rotor also. Correct? If it become weaker due to the for longer operation after 1 year, 2 years, the torque produced by motor will test. This is another drawback. That means due to this or this one, you cannot run this surface mounted rotor based PM motor for a long higher speed. I stop here. I think tomorrow we will continue a little time up. We will see tomorrow. Try to complete permanent these motors, and also another type of motor which is called as BLDC motor, working how it works. Okay. Next week, then we will talk about other chapter. Okay. Thank you. See you tomorrow by 6 o'clock.
Thank you,
Please give
sir.
your attendance
Thank you,
before
sir.
leaving. Yeah. Thank you.
Thank you, sir.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you. Nice.
Thank you, sir.
Yeah.